Not in my class. No. So for an upper bound, you need, exactly, you need a set, right? So I'm going to say, let's call it S, set of real numbers. This is a set of real numbers, set of real numbers, and it has alphas in it. Lots of them, forever. Maybe going this way and going this way. Just like a set of integers, right? They go both sides, right? All right. So we have that. So I'm actually, so what do we need for an upper bound? We need a set that is not empty, right? This is not empty. So we need a set that's not empty. In other words, not equal to and we need our, so these are real numbers, right? Reals. And we need another real number. Let's call it gamma. Is that gamma? Yeah, that's gamma. No, that's not. Yeah, that is gamma. Alpha is less than or equal to gamma. Gamma. Yeah, and then this implies, so this is our formalization of the definition that I'm going to write in a second. So you need a set that's not empty, and we've gone over this many, many times. You need an upper bound. The gamma is upper bound here, right? So, and then that means it's going to look like this. I'm going to put the set S again here. And then gamma is either equal to one of the alphas in the set or bigger. All the alphas are smaller than gamma. Or one of the alphas is the same size. So here, if all the gammas in the set of set S of real numbers is bigger than all the alphas, then it's sitting outside. Otherwise, it's in here. Yeah, your alphas are. Yeah, I was worrying about all this. Like, gammas are not easy to make either. So let alpha, gamma, no, lambda and gamma be real numbers, as in cuts. Okay. And then these numbers are going to be in this set called, and then a non-empty set, we're going to non-empty set S of real numbers, has an upper bound gamma. Okay, so I think we need to write the next line of this too, because the condition is, so the non-empty set S of real numbers has an upper bound gamma, and we've already seen that. Everything in the set S, alphas and let's say lambdas, better be equal to or smaller than that. If they are, then this guy is a upper bound to them. So if this thing is too low, that's the problem. If for any number alpha that belongs to the set S, we have this situation. We have alpha less than or equal to gamma. Draw this first and then add these conditions. So we're going with this one here first. So a non-empty set S, okay. I'm drawing the set S and all on the on Q. So this is S, has an upper bound. So this is Q. And S is full of, if for any number alpha, so the bunch of alphas in here, I mean, it's not wrong, but it's kind of like we want to make it look like this, right? So this is alpha less than lambda when lambda is sitting here. I mean, sorry, gamma. When is alpha less than a gamma? When it's here. When is it equal? Because right here, on here. So yeah, so this is, yeah, so this is, and then this is, and actually, so this one is actually exactly this. It's less than and equal to, or just equal to, right? It's one of the, one is either less or equal, so it's actually equal. And then this is just specifically less.
So do we only use that gamma that's on the thing because that's what's on the
Usually when we have been doing upper bounds, I stick it here because this will end up being the least upper bound. Yeah. So usually I just put it here. And then how have we been thinking about this on the side here? We have been thinking about all this like this with an R. And then you have if let's say, so this is gamma, and we have bunch of alphas in here. Then if gamma is in the set, then it will be right here then, yeah. And if gamma is not in the set, then it's going to be, it'll be looking like this here. Actually, let me redo this down here. So R, we usually think in the real number line, we have, oh, let's say alpha's here, and then this would be gamma. Okay, that's better.
this is all set at.
Yeah, very good.
All right, and then we're gonna make this gamma. Oh, we have two different lines for this.
Yeah, and over there,
So you don't need the upper bound gamma.
oh, so the reason why I have two lines here is that this is the rational number line, with real numbers on it. Here we have a real number line in which this gamma is actually one of the elements. This is the largest number in this, and everything is smaller than that guy. And then here, this is not in the set, but it is the least upper bound. Okay, so this is an upper bound to set S. This is the least upper bound, and it's in the set S. This is an upper bound. This is the least upper bound, but not in the set. Yeah, and here, the set itself is a subset. So we never have, when we're doing rational number lines with, in my notation, when we're doing, when we're sticking in real numbers, they're always like this. They always go in like that, no square brackets.
Yep. And then on the real number line, you can't have square brackets. That's allowed.
Because and also, yeah, this actually, this thing, it shouldn't be red, right? I should not have done that. Let's do, it's always, wait a second, let's see. Yeah, what it should be like this. Maybe. Because it's never really in the set, right?
Yeah.
It never really is. In other words, LUB, oh, I know what's going on. LUB is the real number.
Oh, LUB is A2 in this.
So LUB, in other words, whenever we do this, we have, what's really going on is that a real number represented as a subset of rational numbers, that real number is the LUB of that set. LUB is the, so the real number, represented by a subset of rational numbers, subset of Q,
Funny that fractions don't R.
I know, quotient, because R is for real. So the last big set won the R. So the real number represented by a subset of Q, a real number represented by a subset of Q is the LUB of that subset. And I think I'm not wrong about this. What do you think?
I don't think you're wrong.
No. Okay. All right. Upper bound. So now we're doing the least upper bound definition. So an upper bound lambda, that's when lambda shows up. See, they were using gammas here, right?
Yep.
And as soon, so this is, they switch out, whenever they talk about LUBs, least upper bound, they use gamma. It's called the least upper.
Oh, yeah.
Yes, sir, finally.
Got one right. First time with you ever. I've
For
been here for a while.
S. For the set, I did not get this right. For the set. Because in upper bound, lambda is called the least upper bound for the set S if, so now we can take this off. And do you remember what this thing is?
These stuff is down. Oh, the cut.
It is a cut.
Okay.
As in, it's a
Those gamma, those alpha.
very good. And then this is,
That's our set.
it even says, but it's a set of real numbers that are cuts. Okay, so if for okay, so now we are if for any, so we got an upper bound, and then we are told if for any other upper bound, and I think they're going to go with gamma. So if for any other upper bound gamma, we have this situation. We have lambda is smaller or less than or equal to gamma. And if this is the case, then lambda is denoted by LUB. It is small letter. Yes, it is. S. Okay, so this is Q. We got an S. And then S, so an upper bound lambda is called the least upper bound for the set S if any other upper bound. So let's stick the any other upper bound first. And we're going to make the second picture down here. So this is the picture where lambda is less than gamma. Okay, so let's go back. An upper bound lambda is called the least upper bound for the set S if for any other upper bound, I just put that there, our lambda I'm going to put it right here, yes. And then there you go. Yeah, good. Thank you. I was going to mess this up. Okay, if for any other upper bound, we have it's, yeah, okay. And so this is the first case. And our second drawing is yeah, it doesn't really make sense to make the second drawing, but we'll make it. So here, and then we can say for this condition here, this is lambda less than or equal to. So what if lambda equals the upper?